So, yeah, welcome to pattern analysis. This is our last meeting with actual material. The topic is variational autoencoders. And if you recall our conversations like from somewhere in the beginning of this semester, like one reason, like why should we look into these old methods, why are they relevant, and so on and so on. Like one reason is that they still, like they form the foundation of generative machine learning. And in that context, I think the work on that proposed and what we will be looking at is a paper that has been written a couple of years afterwards to kind of consolidate the findings, but nevertheless, like from the same authors. So this work that proposed the variational autoencoders is a very good example for this. And with the content, like with the material from the class, we will be able to read and understand that paper. And like the main goal for today is that we go through that paper. Yeah? This doesn't necessarily mean that we need to understand like every single like letter or so that is in that work. No? It's not the goal. It also includes a little bit on like deep learning and so on, which clearly has not been part of this class. But the overall concepts, as you will see, essentially make use of the things that we studied in the past 2-3 months. Yeah? Okay, so this is the goal for today. Next week then, we would have, so there will be no meeting this Thursday. Shital is traveling and I thought it's like, yeah, never mind. Next week, we will have a special meeting where I'm not bringing like own content to the table, but we can talk about something that you want. I already have something on my list on the Markov random fields. So I will prepare some clarification for that, for a question that received me. If you want me to address something in particular or to clarify something in particular, you can let me know in advance. But you can also just ad hoc then, like on site, bring something up, and then of course I will try to do my best to react to whatever it is. Yeah? Okay. So this is the goal for next week, and then we're done. Yeah? There is what is missing. There's a remark in the forum I saw this morning that 2 videos are missing. I'll add them. Like 2 videos from the last Mondays are missing. I'll add them. I'll link them to the class here. Sorry for the delay, but I probably only do it tomorrow when also this video here will be available, and then we have the full collection. Okay, so the paper that we're going to talk about is the one that is here available in StudOn. An introduction to variational autoencoders. It's a long paper, but we only look at the beginning, like only at the first 2 chapters. And if we just look at the table of contents, the first chapter is an introduction, and I think this is very literally an introduction, but it's going to be helpful, so we look at it. The second chapter is on the variational autoencoders themselves, and then the third and fourth chapters, they add a couple of details like beyond Gaussian posteriors and deeper generative models. I think they are not super relevant for us, so So this is why we look at the first 2 chapters. In order to make this a bit more convenient on my side, let's switch to a different, like a more like physical representation. So we look at the paper like this. First of all, if maybe some of you attended a deep learning class or so and heard about a variational autoencoder, maybe some of you didn't. In a nutshell, if we want to look at a variational autoencoder, there's a particular visualization on page 17 of the paper that visualize, it's cut off, I'm sorry. Can I change this? Yep, this way. So in the paper, they visualize it like this. So the yellow highlighting is by me, sorry. So there's a data set D in a weird manifold, and data is denoted as X. And then they say, okay, there's a encoder, Q, with parameters phi, that gives a distribution of latent variables Z given some input X from the data set. And then there's this latent space, the Z space, endowed with a prior distribution for Z, with this model P parameterized by theta. And if you have latent variables, then you can pass them to a so-called decoder, which is denoted here as this distribution P with parameters theta of, again, the data space X given the hidden variable Z. Yeah? Maybe if you attended a deep learning class, maybe this was not the way how you drew or how you looked at a variational autoencoder. Yeah? Maybe you looked at, or maybe someone visualized a variational autoencoder like this. Here would be the data space. So here's an X. And then this would be the encoder. Q theta, what is it? Phi, Q phi Z given X. Here's the latent space with the Z. And here's the decoder. P of theta of X given Z. Yeah? And the way why someone might have written it like this is because maybe X is an image, yeah? Then it has like, I don't know how many pixels, many. And you feed it, for example, to a neural network with a certain like input dimension, high input dimension, no? to accept the image. And then in this neural network, the layers, they get narrower and narrower, such that this space here, this is a smaller, it's like a bottleneck. No? It's a smaller vector of latent coefficients. So in a way, it's a compression, and this is what this triangle visualizes. Yeah? And then if you have such a hidden variable, the decoder restores it to an image. Yeah? So this is why, like from only a couple of coefficients, it, in a magical way, it creates an image out of it. Yeah? And this is a very, very, very fruitful paradigm in generative modeling, no? Because essentially you force the machine learning system to learn a compressed representation, to compress the information, no? And then it successfully learned that compression if it's able to reconstruct the same information again. So when you train such an autoencoder, you can say, if I put input X here, how different is it from the output X prime? And any deviation from that I can take as an error that I use to improve the network, yeah, in a loss function. So this is a convenient, like conceptually from a data modeling perspective, this is a very convenient property of a variational autoencoder, no? Because you can say, okay, all I'm doing is I put an input image here and I reduce it to very few coefficients, and then I see, can I get the same image or the image with only small errors out again? And I try this, of course, for different images. Otherwise, it could just memorize, yeah, you know, it's a cat or so. So you try it with different images, and then hopefully it works for all of these images. Yeah? So here, in that picture, in our paper, it's circularly drawn. But here it also becomes a circle if we take that link here and say, okay, this is the one data manifold here. No? It's just not tied together here in the end. Yeah? Okay. So who has heard about an autoencoder before? Okay, so limited number of people. Let's have a look at it from, like a closer look from a mathematical perspective, but let's go through the paper from the beginning. Okay, so we have these two chapters, yes. I think it's actually worth to more or less read the paper, or at least the biggest part of it. What is occluding my lens? Okay. Because it also provides a bit of justification, like why are we doing all this stuff? Huh? So let's have a look. One major division in machine learning is generative versus discriminative modeling. While in discriminative modeling, one aims to learn a predictor given the observations. In generative modeling, one aims to solve the more general problem of learning a joint distribution over all the variables. Yeah? So this is why we're looking at all these joint distributions all the time. No? And we have the observations, x, some form of x's usually, and then some hidden variables, which can be y or z or so. No? Okay. A generative model simulates how the data is generated in the real world. Modeling just is meant in a scientific way, no? In almost every science as unveiling this generating process by hypothesizing theories and testing these theories through observations. Okay, let's go on. Now I know what is occluding. Okay. There are many reasons why generative modeling is attractive. First, we can express physical laws and constraints into the generative process. Yeah? Yeah? You can't see it. No, you can't. I'm sorry. I have to learn it. In every lecture hall, there's a different mechanism to project things. So let's not push it taller than this, then it works. Okay, so there are many reasons why generative modeling is attractive. We talked about this. No? We said, okay, if I have a joint model of x and z, z are the latent variables. So this should be the underlying mechanism that is responsible for making these observations. Yeah? So this is the idea of the this is the reason that we're looking at these two variables together. No? And in discriminative modeling, we would just say, okay, let's straight shoot for the hidden reason, no? the latent variable, whatever. Okay. So another reason is trying to understand the generative process of data and that it naturally expresses causal relations of the world. So this really then goes into the direction of the graphical models that we looked at the beginning of the semester. No? That you say, okay, if an alarm has been triggered, no, it could have been a burglar, it could have also been some sort of earthquake that just happened to be in the area and that triggers the alarm. No? To turn a generative model into a discriminator, we need to use Bayes' rule. So how do we do this? Well, we just write it somehow like this, no? and then we're good. No? There's our discriminator. For instance, we have a generative model for an earthquake of type A, another for type B, and then seeing which of the two describes the data best, we can compute a probability of whether earthquake A or B happened. This is not even necessarily normalizing by X. No? This is like what the author is describing here. It would be sufficient to only look at the numerator and then go for the more likely possibility out of these two. No? Yeah. Applying Bayes' rule is, however, oftentimes computationally expensive. In discriminative methods, we directly learn a map in the same direction as we intend to make future predictions in. This was this like shooting directly for, give me the input and tell me what I need to classify. No? For instance, one can argue that an image, this is in the opposite direction than the generative model. So in the generative model, as you may recall, is that we say there's this hidden reason, and this reason creates observations, whereas in the discriminative scenario, we say, okay, give me the data, and I map it. I just map it onto the reasons that you give me. No? Okay. For instance, one can argue that an image is generated in the world by first identifying the object, then generating the object in 3D, then projecting it onto the pixel grid. A discriminative method model wouldn't bother about this. It just takes these pixel values directly as inputs and maps them to the labels. Okay, I think we're familiar with this, I suppose. While generative models can learn efficiently from data, they also tend to make stronger assumptions on the data than their purely discriminative counterparts, often leading for higher asymptotic bias when the model is wrong. What assumptions might this be? Why do models make stronger assumptions? Generative models, stronger assumptions on the data? At what opportunity? Because we're training what? The training set. It's not due to the training set necessarily. It's about it's inherent to this distinction, to this versus this. So if you say I'm starting from a root cause, and this creates a tangible artifact, then you need some form of, I don't know, this is not a nice way to write it, but let's do it nevertheless. You need some path, like how should I possibly get from this reason to the observation? Yeah? So in there you have to put something in. So either knowledge, if you have knowledge, it's fine, no? Or some assumption where you say, yeah, it's not a harmful assumption, it's probably going to be fine. No? So here are restrictions, whereas here there's nothing like that. No? You just say, oh, I look at it, it looks like a cat. So there's not necessarily an assumption here, or at least it's not an assumption that is as complete as, if I have an underlying reason for seeing a cat, then somehow there might a cat come out of this. No? So this is the thinking behind that. No? Yeah, so while generative models can learn efficiently from data, they also tend to make stronger assumptions on the data than their purely discriminative counterparts, often leading to higher asymptotic bias when the model is wrong. For this reason, if the model is wrong, and it almost always is to some degree, if one is solely interested in learning to discriminate, and one is in a regime with sufficiently large amount of data, then purely discriminative models typically will lead to fewer errors in discriminative tasks. No? I think this is a very basic statement in machine learning, no? That these generative models, they are not as accurate, they have a lot of problems and so on. If it's about results, why don't you go for a discriminative model? No? What is the angle about the data in the generative models? I'm not sure whether you're familiar with this. It's something about Bayes' formula, because if you have a prior here on the distribution, then in situations where you don't really have a lot of statistics, oh, sorry, I should have written it like this here in this writing. If you have a prior, then you can make up for insufficient statistics here on your observations. No? So the prior can just take over. And you also in scenarios with very little data, if your model is good or your assumptions are good on the generative process, you can also get very nice results on very little data. But as soon as you have a lot of data, then this doesn't bring a tangible benefit anymore. Okay. Yeah, in the generative modeling can be useful more generally. One can think of it as an auxiliary task. For instance, predicting the immediate future may help us build useful abstractions of the world that can be used for multiple prediction tasks downstream. This quest is for disentangled, semantically meaningful, statistically independent and causal factors of variation in data is generally known as unsupervised representation learning, and the variational autoencoder has been extensively employed for that purpose. Okay, what does that mean? So unsupervised representation learning. No? This is exactly this scenario that you say, okay, I have an image. I don't even need a label necessarily, because all I'm doing is I take this image, squeeze it in here, and see whether whether it can be reconstructed. No? So this is inherently unsupervised. So I don't even need to know whether this is a cat or not. No? I just care about the ability to reconstruct the very same image. And while at first glance this might look like a zero solution, no? It's okay, I have a cat, I get a cat. What you're actually forming here in between are two models. So one model that can be used as a discriminator, no? It gives a distribution of latent labels, if you classify, for example, no? Given an input. So you can form a cat classifier maybe out of this. And here, if you take the prior times the decoder, this is a generative model. So this is the joint distribution effectively. No? It's also very, very nice. Yeah, so where were we? Alternatively, one may view this as an implicit form of regularization. By forcing the representations to be meaningful for data generation, we bias the inverse of that process, which maps the input to a representation into a certain mold. The auxiliary task of predicting the world is used to better understand the world at an abstract level, and thus to better make downstream predictions. I think this is still discussing this construction that at that time the readers kind of had in mind because they already knew the variational autoencoder construction. No? Okay. Anyways. The variational autoencoder can be viewed as two coupled but independently parameterized models. The encoder or recognition model, this would be the left side here, and the decoder or generative model. These two models support each other. The recognition model delivers to the generative model an approximation to its posterior over latent variables, random variables, which it needs to update its parameters inside an iteration of expectation maximization learning. Reversely, the generative model is a scaffolding of sorts for the recognition model to learn meaningful representations of the data, including possibly class labels. What does that mean? What does that meaning? That sentence mean? Reversely, the generative model is a scaffolding of sorts for the recognition model. So the recognition model was the one on the left. So this is a scaffolding of sorts for the recognition model to learn meaningful representations of the data, including possibly class labels. I don't know. I stumbled over this sentence when I first read it. What might it? What could it mean? Any hypothesis? Yes. Yes. Yeah, I agree. I'm pretty sure this is what they mean, no? Like, by the possibility to recreate this image from the latent space, we have a tool to kind of verify that the encoder was doing what it was supposed to do, like to have a meaningful compression of the information and like throwing away, because something has to be discarded. These are much less coefficients, so something has to be thrown away. But with the possibility to decode this again, we can check, did it actually throw away information or content that was not critical information for the reconstruction? No? Yeah. Mm-hmm. Good. One advantage of the variational autoencoder framework relative to ordinary variational inference, as we discussed it in the class, is that the recognition model, also called inference model, is now a stochastic function of the input variables. This in contrast to variational inference, where each data case has a separate variational distribution, which is inefficient for large data sets. Yeah, we did not discuss this angle about the variational inference at all, so don't be concerned about it. Yeah. The recognition model uses one set of parameters to model the relation between input and latent variables, and as such is called amortized, I'm sorry, I'm butchering this word, inference. This recognition model can be arbitrarily complex, but is still reasonably fast because by construction it can be done using a single feed-forward path from input to latent variables. Yeah, I think this is this has been written by someone who does have a neural network in mind, talking about a single forward path, just meaning, okay, I put in this image, I have these layers of the neural network, and then zack, I'm there in this latent space. No? Okay. However, the price we pay is that this sampling, the price we pay is that this sampling induces sampling noise in the gradients required for learning. Perhaps the greatest contribution of the variational autoencoder framework is the realization that we can counteract this variance by using what is known as the reparameterization trick, a simple procedure to reorganize our gradient computation that reduces variance in the gradients. For sake of completeness, I'm going to show you this reparameterization trick, but we cannot really appreciate it because we haven't really talked about the training of neural networks. And it's a feature that helps training this as a neural network. No? So in that sense, it's not really, even though the authors here write, okay, this is maybe their biggest contribution, we have to say, okay, it's maybe the one that we cannot really make use of here, but I say it's fine. No? Okay. So what is better for us is this statement. Variational autoencoders marry graphical models and deep learning. The generative model is a Bayesian network of the form. We have here a likelihood and a prior, or if there are multiple stochastic latent layers, a hierarchy such as a likelihood with some priors, and then these priors again depend on hyperpriors, and you could sort of stack a model like that. No? Oh yeah, here. Similarly, the recognition model is also a conditional Bayesian network of the form, the latent variables given the input, or as a hierarchy, we can also have a stack of latent variables given some input x here. But inside each conditional may hide a complex deep neural network. And this is what makes the model flexible enough to solve interesting problems. So it's not just from a mathematical perspective interesting, but also from an applied perspective. No? So for example, getting this posterior here, the latent variables given the input, this can actually be a neural network that has as input the image and some additional noise, which we will discuss when it comes to this reparameterization trick. Yeah, so in that sense, the learning is a mix of classical expectation maximization with a neural network, so the backpropagation that is used, or that is the standard training algorithm for deep neural networks. Okay. Right, so here they're just repeating themselves. So the framework of variational autoencoders provides a principled method for jointly learning deep latent variable models and corresponding inference models using stochastic gradient descent. Backpropagation is the algorithm that trains a neural network, that calculates the update for neural network weights. And stochastic gradient descent is like a wrapper, you could say, around the backpropagation in order to train only on a couple of some entries of the data set at a time, because you cannot load everything into memory. No? Okay. Questions so far? It's okay. No, it's still rather abstract. No, I mean we haven't looked at specific math. We also haven't looked at we haven't looked at anything. But it's more like a conceptual framework. No, arguing for the benefits of the strong sides of generative models. Probably this unsupervised idea of training the encoder and the decoder jointly. No? Let me quickly go through the remaining chapters of the introduction, just to cover, because it covers a little bit of ground of what we had in the class, and then we can look at the actual method. Yeah? Okay. So probabilistic models and variational inference. As probabilistic models contain unknowns and the data rarely paints a complete picture of the unknowns, we typically need to assume some level of uncertainty over aspects of the model. The degree and nature of this uncertainty is specified in terms of conditional probability distributions. Models may consist of both continuous valued variables and discrete valued variables. The, in some sense, most complete forms of probabilistic models specify all correlations and higher order dependencies between the variables in the model in the form of a joint probability distribution over these variables. Yeah, okay. I mean, this is an aspiration, no? I mean, in practice, we do what we can in terms of relationships that we can represent in such a model. Okay. So X are the observations, just written in a vector. And we assume, I think this is, for cultural reasons, this is an important sentence here, because it's oftentimes implicit. We assume the observed variable X is a random sample from an unknown underlying process, whose true probability distribution P star of X is unknown. We attempt to approximate this underlying process with a chosen model P theta of X with parameters theta. So, yeah, I think that's the, this is like very, very clearly spelled out, I would say, this attempt to model reality by means of machine learning models. And then learning is most commonly the process of searching for a value of the parameters theta such that the probability distribution function given by the model approximates the true distribution of the data denoted by P star X, such that for any observed X, these distributions are approximately the same. No? Okay. Yeah, and you want this your parametric model to be sufficiently flexible to adapt to the data, and at the same time, we wish to be able to incorporate knowledge about the distribution of the data into the model that is known a priori. This is the idea of the generative process. Yeah? Okay. Okay, we are briefly mentioning conditional models. We can cut this short. No? Conditional model is one that approximates the underlying conditional distribution P of y given x, a distribution over the values of variable y conditioned on the value of the observed variable x. And yeah. Right, and then of course you can use a neural network as a universal approximator to parameterize such a conditional distribution. I think don't really need to go into details here because we're not talking about neural networks too much. But I think we can say a neural network has the capability to model such a distribution. This is what we will need for today. Okay. Then we have the concept of the directed graphical models in conjunction here with the neural networks. You are familiar with with directed graphical models from early on in the lecture. No? So a joint distribution factorizes into smaller distributions that consist of variables xy, xj, whatever they are, given the parents of xj. So the conditional distributions here are the directional arrows in our graphical models. No? So if this is xj, these are the parents, no? Then could say, okay, there's a probability xj given x1 and x2. Okay. Yeah, and here's an interesting sentence. Traditionally, each conditional probability distribution xj given the parents is parameterized as a lookup table or a linear model. This is maybe a bit of a disappointing truth, but it is exactly like that. No? That the actual distribution, oftentimes that people then use to implement this, can be super simple as a lookup table. No? And it doesn't need to be anything fancy. No? But of course, you can also plug in a neural network instead, and then much richer functions can be modeled. Yeah? Okay. Okay. For the data, yeah, if you assume independently and identically distributed data, the advantage is that you can treat every data point separately. So this is also an expression that if you say you're interested in the distribution or the log distribution here of the whole data set, if you're dealing with IID data, then you can split this up into a sum in the logarithmic space or without the logarithm into a product of the probabilities of every individual data point because there's no connection between these. Yeah? So this is the idea of the IID, the independently and identically distributed data assumption. No? We briefly discussed this when we talked about the random forests. No? So there the bagging didn't come with IID data. No? Bagging is only, what is bagging only? Do you know? Yeah. Bagging uses different subsets of the data, yeah, and it's only identically distributed. Then it's not independent because these subsets may overlap between different trees. No? Okay. Let's jump to the maximum likelihood. Most common criterion for probabilistic models is maximum likelihood. As we will explain, the maximization of the log likelihood criterion is equivalent to minimization of a Kullback-Leibler divergence between the data and the model distribution. So this hints now in the direction of this. We had this trajectory in the lecture with the expectation maximization algorithm, then the generalized expectation maximization, which was a bit abstract, and then the variational inference following up, where we had this Kullback-Leibler divergence as a criterion in the optimization process. Yeah? Okay. For the training of neural networks, the stochastic gradient descent can be used, but let's skip this part because, again, it's about the neural network training. Here's a very brief section about Bayesian inference. From a Bayesian perspective, we can improve upon maximum likelihood through maximum a posteriori expectation, or going even further, inference of a full approximate posterior distribution over the parameters. We also discussed that. Okay. Now they have a little helper construction here, where they say, and this is what they discuss in this and the next, like these two subsections here. If we have perfect knowledge about some task, so we know all the observations, we know all the latent variables, somehow we know the generating process, whatever, then it is no problem in principle to learn a model, as they call it, a deep latent variable model, to train a deep latent variable model that uses a neural network to represent this distribution. They didn't first define the marginal distribution. We're familiar with this, talked about it. And then you can say, okay, if you want to train a neural network here, you could, for example, say the simplest way to decompose such a joint distribution is to say you need a model for the prior distribution and you need a model for the likelihood. Okay. Then there's an example with Bernoulli data. We can skip it. And now we come to the problem with that. And finally, then we can talk about the variational autoencoder. So the problem, always when we are dealing with these latent variable models, it's always the same difficulty there. No? The main difficulty of maximum likelihood learning in these deep latent variable models is that the marginal probability of data under the model is typically intractable. The marginal probability of data is a complicated expression to just say the P of X. Yeah? Why is it called marginal probability of the data? Because if we take the joint model, you can see this, no? Yeah. If we take the joint model P of X and Z, then the distribution of X is obtained by integrating over all possible instantiations of the latent variable. This is the marginalization. Yeah? So the marginal probability of the data under the model, this means that you have, for the integral, you have to come up, either you have to enumerate all possible states for Z, which is usually, these are, even in a discrete model, these are exponentially many. In a continuous model, there might not be any perspective for this. No? So this is what makes everything there, brings it close to intractability to solve it exactly. No? So, and this is responsible for, not having an analytics solution or an efficient estimator. And due to this intractability, we cannot differentiate it with respect to its parameters, which is a killer argument for neural networks because the stochastic gradient descent effectively based on differentiation. So the intractability of P of x is related to the intractability of the posterior distribution of the hidden variables given x. So even if you can calculate the joint distribution of x and z efficiently, then you still have this problem that the posterior you get by dividing the joint through this through the evidence, no? Or the evidence you could obtain by dividing the joint through the posterior. So if posterior and evidence are not available, then you cannot, like you can't get either of those. No? So this is what they're trying to say. So since the joint distribution of x and z is tractable to compute, a tractable marginal likelihood P of x leads to a tractable posterior P of z given x and vice versa. So this is the positive statement. If we could get one of those two, then we could also get the other. And this is where the autoencoder will do the approximation. No? Yeah. Approximate inference techniques allow us to approximate the posterior and the marginal likelihood in these deep latent variable models. This is not possible, let's say, with traditional inference methods. Okay, so we're done with the introduction. Yeah. Okay, so what did they say? So what were the key hypotheses? So one, I think, basic hypothesis that we just have to live with is it's useful to have a generative model. Yeah, I mean, okay. And then in that generative model, you somehow have to fill these quantities here to make it meaningful or to make it somehow useful. You have to calculate the posterior. They write here the likelihood in the prior, they write just as the joint distribution, and the evidence. No? You need to have access to them to use this really as a generative model. And then they said, okay, but we have a problem. So it may be possible to learn this joint distribution here, but this P of x is computationally intractable because it's an integral over the whole latent space. And this posterior here, we also don't really get it. If we would get one of those, we could get the other by just rearranging the terms of this equation. Yeah? So this is the state in which we are after the introductory section. And by the way, we did a detour over the probabilistic graphical models and like whatever there is out there. No? Okay. Let's have a look at the variational autoencoders, finally. This section, let me just show you for some orientation, let me show you the table of contents. So we sort of ran through the introduction. And the variational autoencoders, they focus on this encoder part here for quite a bit. Yeah? So we talk about the encoder. The evidence lower bound will be in connection with the encoder. Stochastic gradient-based optimization of the elbow sort of links up to the elbow again, and the reparametrization trick. So here we are kind of working on the encoder part. Factorized Gaussian posteriors. Again, posterior is the encoder. So still here we are talking about the encoder. And only in 2.6 is the estimation of the marginal likelihood, which is then this part or this part, I guess. Hold on. Yeah, we will see. All I want to say is our attention goes now to the encoder and how the encoder can be modeled. So claim, the framework of variational autoencoders provides a computationally efficient way for optimizing these deep latent variable models jointly with a corresponding inference model using stochastic gradient descent, so the training method for neural networks. To turn this intractable posterior inference and learning problem into tractable problems, we introduce a parametric inference model Q, parameterized with parameters phi of z given x. This model is also called an encoder or recognition model. If you recall the reasoning, like after we did the clustering for the Gaussian mixture models, no? Said, okay, like what could we do something to make it more flexible, maybe that it automatically adapts to the number of clusters, no? For the Gaussian mixture model. And then turned out it's not so easy because things become intractable, and we had two choices, like two paths to follow. No? One was to say, okay, you can do inference approximative. You have to do some approximation. There are two possibilities for approximations. No? One was to use something like a Markov chain Monte Carlo model. No? And sampling-wise, like sampling in the solution space effectively to approach a solution that is a reasonably good approximation. And the other possibility was to use a variational inference, which takes a different approach. It says, okay, the function is too complicated. I use a function of my liking that I can optimize a little bit better. But by this choice of this function that is better for me, I already make an error, yeah? An approximation error. But it's okay, I pay it. And then I have a function for which I can solve this. And here we are following this line of reasoning, no? That we say, okay, let's fit a model Q. And this model Q with its parameters phi, it will be easier for us to work with that. So this is the line of reasoning that the variational inference was using. No? It's just that we give it a new name. Now it's called an encoder. No? Okay. With phi, we indicate the parameters of this inference model, also called the variational parameters. We optimize the variational parameters phi such that this model that we want to use hopefully is a good approximation of the model that we should be using, but we can't because of tractability. As we will explain, this approximation to the posterior helps us optimize the marginal likelihood. Okay, so let's go. Yeah, here's a nice remark. So this inference model could be any directed graphical model, but in fact we will be using a neural network. And then we come to this variational formulation, no? The evidence lower bound. So what is the idea behind this? The idea is this. We have there's this model P parameterized by some hypothetic parameters theta that we really would love to work with, but we can't. So we say, okay, not a big deal. We use this model Q, parameterized by parameters phi. And for this model, it's really nice. We have a nice training process and so on and so on. Yeah, and the only thing that we have to make sure now in this training process is that in each training iteration we come closer to P. So our approximation of P becomes better in every step. This is the only thing that we have to take care of. And this is what the evidence lower bound helps us with. Yeah? So if P, no idea what P looks like because it's intractable and everything. Yeah? But if this were P, yeah, and if Q is anything else, like whatever we start with, all we need to make sure is that in every iteration, Q becomes a little bit more similar to P. And this is what can be shown with this decomposition into the evidence lower bound and the Kullback-Leibler divergence. And this is what is going to follow here. Yeah? Okay. So I'm just saying this because I know that it looks very heavy, like there's a lot of math involved, no? But I think the objective, like the reason why this is done, is actually very simple. It's to reduce the difference between our approximation and the goal of what we actually want to approximate. Yeah? Okay. So the optimization objective of the variational autoencoder, like in other variational methods, is the evidence lower bound, abbreviated as ELBO. An alternative term for this objective is variational lower bound. Yeah, I think they are very kind to always restate all the possible names in the community, but it's not really necessary. Okay. Okay, ELBO is oftentimes derived through Jensen's inequality. They avoid it. Okay. So here's their derivation. For any choice of inference model Q, so whatever Q is, including whatever choice of variational parameters phi, we have, and this is something that in one way or another we also have somewhere in our slides. So it's a very, I would say, canonical way of deriving things. So you start with the evidence, the probability for the data given some model theta, but now we are using the Q. So the subscript Q here is really important. So we are interested in the expectation for coming to this, let's say, P by means of sampling from Q, because Q is all that we have. Yeah. Okay, and then one can rewrite this just by, this is a direct application of, direct application here of the base equation. No? Instead of P of X, we can also insert the joint distribution divided by the posterior. So it's just rewritten. Then, and this is for P. And then you can expand it by Q of Z given X, here, and split it up. And then the expectation is a linear function, so you have it here, you have it there. And then you have these two terms, yeah, where one is this famous evidence lower bound, and the other one is the Kullback-Leibler divergence between our model Q for the posterior and the actual desired model P for the posterior. So this is the mistake that we are making in our approximation here. Yeah? And it turns out, so the Kullback-Leibler divergence is larger or equal to 0. So it's a positive gap that we have. And this means that the evidence lower bound, it is the evidence, but it's a little bit lower than the actual evidence. So this is why it's called evidence lower bound, because there's a positive term missing, and this is the Kullback-Leibler divergence. Yeah, maybe you recall from the variational inference chapter that we discussed, or if you don't, then maybe this part is helpful in sort of looking at it from a different angle or so in order to work through this. Okay. Yeah. The first term is the variational lower bound, also called evidence lower bound. So this term. And due to the non-negativity of the KL divergence, elbow is a lower bound on the log likelihood of the data. Okay. So what can actually be reduced is, oh, sorry. I'm sorry. Did I break it? I did. Come back. No. It's coming back. So if we minimize the Kullback-Leibler divergence, then in that process, we get closer, like the evidence lower bound has to grow, so we get closer to this desired goal. So we're reducing, so we do exactly that from iteration to iteration, we get closer to this function that is otherwise difficult to deal with. Yeah? Okay, and this is what is prepared here. So interestingly, the KL divergence dKL between Q and P determines two distances, and it's a crime to write distances because it's not a distance. But okay, I mean, let's not be unfriendly to others. By definition, the KL divergence of the approximate posterior from the true posterior, yeah, so the difference between these two distributions, and the gap between the evidence lower bound Lx and the marginal likelihood log P of x. This is also called the tightness of the bound. And the beta Q approximates the true posterior distribution P, Q of z given x, P z given x, in terms of the KL divergence, the smaller the gap. Okay, so in any case, it is just a good thing to minimize the Kullback-Leibler divergence. This is what they're saying. Yeah? Okay. Yeah, so just to drive this point home, they effectively repeat it here. No? It can be understood that maximization of the elbow with respect to the parameters theta and phi will concurrently optimize the two things we care about. It will approximately maximize the marginal likelihood P of x, so we come closer to this. This means that our generative model will become better. It will minimize the KL divergence of the approximation Q of z given x from the true posterior P of z given x. So also this approximation of the posterior becomes better. Okay. And now they say, let's do a stochastic gradient-based optimization of the elbow. So in that framework of the neural networks. Yeah? And this is where we will get a little bit unsharp because, again, we have a bit limited knowledge about neural networks. But let's briefly look at it, nevertheless. An important property of the elbow is that it allows joint optimization with respect to all parameters phi and theta using stochastic gradient descent. We can start out with random initial values of phi and theta and stochastically optimize their values until convergence. So these parameters theta and phi, they actually occur in the evidence lower bound here of the data. Okay. And what they will show here is that they can use the stochastic gradient descent in mini batches. Let me skip this. Oh, they use a Monte Carlo estimator as they go. Do you recall this application of the Monte Carlo estimator if you want to evaluate an expectation? I think it's an important use case in doing inference. If you want to evaluate an expectation of some variable distributed, no? With respect to some function f of z, yeah? Then and this has to be a sum or integral, depending on whether you're continuous or discrete. So this would be the expectation of, like, for a variable z drawn from p of z of f of z. Yeah? And now, oftentimes, it can be a problem to evaluate this expression, but it can be feasible to sample from this p of z. So you can do something, draw like 10 or 20 samples, and whatever z you draw here, you plug it in here into this function and evaluate that function for these 10 or 20 locations. And just calculate an average out of this. Something is not right in this equation. But anyways, if you calculate an average then from these 10 or 20 samples, you get an approximation, a sampling-based approximation for the actual expectation of that function. And this is a very useful trick that is tremendously oftentimes used. And this is also what is used here within these equations. But let's skip this nevertheless in the interest of time. Okay. Now, let me briefly tell you what the reparametrization trick is, just because they advertised it as a big feat. And it is certainly a nice trick, but again, we're not talking about neural networks. So here's a visualization of the reparametrization trick. If we look at our encoder-decoder model, so if you follow that model naively, or maybe we can just read the text that is written down here. Illustration of the reparametrization trick: the variational parameters phi affect the objective f through the random variable z, which is drawn from q, z given x. We wish to compute gradients to optimize the objective with stochastic gradient descent. In the original form, we cannot differentiate f with respect to phi, because we cannot directly backpropagate gradients through the random variable z. What does that mean? So this, what this encoder gives us is actually not a scalar value, but it's a distribution, yeah? A distribution of the latent variable z. No? Okay. Now, so we pass the image in here, and we get some other image out here, and in order to pass through here, we have to draw a value from that distribution. No? So if we would just naively backpropagate this, then it wouldn't be possible to calculate a gradient here, no? Because it says, oh, to somehow sample from some mean and some standard deviation here. This is going to be a Gaussian distribution. No? We have to sample from a mean and standard deviation, and then based on that, it has to be passed back further. And this doesn't work if this is a random variable that is drawn from a mean and a standard deviation that are actually the model parameters here of our model. And the reparameterization trick, what it does is that it says, okay, look, the gradient doesn't have to go through a randomly sampled variable, but instead you can introduce a placeholder function where you draw a sample in the forward path, you store it, and then it's a fixed value that you have here. So you can backpropagate through that function. Then you're independent of epsilon, so you can, and at that point it's a fixed value anyways, so you can backpropagate your error to phi and x. And so it works, yeah? Which certainly is a nice trick to make things happen, but again, we are lacking a bit the background to appreciate it, so let's not bother about it at this point. Yeah? Okay. Okay. Which solves many problems, because at the end of the day, we can say, okay, so apparently there is a mechanism then to update these values for the evidence lower bound, and this gives us an approximation Q that iteratively approaches the solution. Why does it approach the solution? Because it's an unbiased estimator. So if we only put in enough resources, our approximation will be close enough to the true solution. This is what unbiased estimator means in practical terms. Yeah? Okay. Good. Yeah, there is another technical detail then that comes with the reparameterization trick, and this is that you have to consider the determinant of the so if you make a change of variables from a latent distribution Z to this variable epsilon that is part of the reparameterization, you have to include the determinant of the Jacobian, which is a technique that is known to optimization people, but also I would like to skip it. And then finally we come to this point. What distribution should we choose here in the center? And what is actually very commonly used for variational autoencoders is that they say, let's just take a Gaussian distribution, no? With a very simple, for example, a diagonal covariance matrix or so. It's fine. There's another subsection that says, okay, you don't need to go diagonal, no? But you can. In many applications, it's just fine. And then what you have here is a Gaussian distribution in so and so many variables, depending on how large you want to choose your latent space, maybe 700 dimensions or so, no? But it's much less than the input dimension of the image. And with that, it's a nice model, nice in the sense also that it nicely interpolates between neighbored locations in that Gaussian. No? So you can literally sample, if you want to generate a new image, you can throw a dice, like a sample from that Gaussian, and you end up at some location here, and then it interpolates essentially from that learned knowledge and gives you a new image out here. No? So this is the sampling aspect of a variational autoencoder, or you can use the encoder as a classification, like a representation on top of which you build a classifier in order to distinguish different objects or so that you have in the image. Okay. I'm a bit carefully looking at the clock, but I think I'm also more or less through with what I wanted to show to you. So maybe we just call it an end here. And yeah, I don't know. I hope you enjoyed this a little bit, because I think it kind of, like, to me, it shows that these old techniques, no? If you say, okay, the Markov chain Monte Carlo, or like whatever, this is all old stuff, no? It's all 1900 something, no? 1900 so and so. But it's not so that it's forgotten. No? It lives on. No? People build these models based on these techniques, reusing the very same arguments that people were using a long time ago. No? And I think this is, I think it's just, particularly now with all these generative models that are actually like in production use, no? I think it's hopefully it's kind of clear, no? that this is like just part of the genetics, no? of these like generative models. What we have been doing in the class. No? Okay, so yeah. I think I'm done for this semester. What are your questions? Okay, so be sure to collect some questions until next week, because this will be the last time that we meet. I mean, except if you happen to be in the same lecture hall for the exam than me, then of course we meet a second time. But then I mean, next week will be the last time that we can like talk to each other, no? in a normal way. Okay. So then thank you and see you then.